Good afternoon, everyone. In the previous lecture session, we had seen some of the examples 5.11, 5.12, and 5.18. And I told you that we'll be covering the next question, that is 5.13, which is an important question. We'll be covering it in the next session. So now, in today's session, let us start solving the question 5.13 from our textbook. Let us have a look at the question. Assume that the first six memory reference instructions in the basic computer listed in table 5.4 are to be changed to the instructions specified in the following table. So see, we have studied a list of memory reference instructions. You are now asked to change those instructions. You have to make your own instructions which are given over here in this table. So here we have specified six different instructions with different opcodes. Okay. Let us continue with the question. Assume that the adder and logic circuit in figure 5.4 can perform the exclusive OR operation. That is AC equals to AC XOR DR. So apart from the operations that we are doing, you also have an operation called AC XOR DR. Okay, this thing is also available in your ALU. Assume further that the adder and logic circuit cannot perform subtraction directly. So if you are asked to perform subtraction, subtraction cannot be performed directly. Instead, what you'll have to do is you do not have a subtractor where you simply provide two operands and it will calculate the subtraction. It would be calculating the difference. Okay. So here, how would the subtraction be carried out? Subtraction must be done using 2's complement of the subtrahend by complementing and incrementing AC. Okay. Uh, Give the sequence of register transfer statements needed to execute each of the listed instructions starting from timing T4. We know that all our memory reference instructions start from timing signal T4. T0, T1 is for fetch, T2 is for D4, T3 is for fetching the effective address. So the execution of instruction starts from timing signal T4. Okay. So now, like we saw how to see, recall the concept. We had seen the memory reference instruction. If you are asked to write the memory reference instructions, sorry, what happens in a particular memory reference instruction? We had seen that first instruction, memory reference instruction was AND. Okay, so how did we write? We saw like this, that D0 is the code for AND. At timing signal T4, what operation takes place? We first need to bring the operand to DR. And then at D0 T5, what did we do? AC equals to AC plus DR. And now this AND task plus nahi, sorry, this is AND. So AC equals to AC and DR, and then we set the sequence counter to 0. So this was the sequence of register transfer statements required for performing AND. Similarly, we saw it for all the memory reference instructions, that is AND, add, load, store, bun, BSA and ISA. Okay, so in this question what they have asked us to do? They have asked us to formulate such register transfer statements, sequence of register transfer statements that are needed to execute each of these instructions. Okay, so one by one we'll be writing instructions for each of these. So let us start off with the first one. First is XOR. Okay, we are asked to perform this thing. Okay, what is the opcode over here? 000. So that is D0. When does this particular instruction start executing at? It starts executing at timing signal T4. So what? This would be my control function. Okay. Now here what we need to do is we need to XOR AC with the memory word. Okay. Here EA stands for effective address. So whatever is it in memory, we need to XOR it with AC. Now we know that we cannot perform any operation directly on memory. So what we need to do is we need to first bring that operand to DR like we did it for AND and ADD. Okay, so here also we do the same thing. So in the first step, D0, T4, what will we do? We will bring the operand specified by the effective address to DR. Now once the operand is there in DR, what is the next step? D0, T5, simply carry out AC is equal to AC XOR DR. Here it is given that um, XOR operation is available in your ALU. Okay, so I can directly perform XOR here with the two registers AC and DR. And along now this task is done, XOR exclusive or to AC done. So what we'll do? We'll set the sequence counter to 0. So this is my first instruction. Okay, now let us see the next one. What is next one? ADM. ADM is what? Add AC to memory. We have to add the content of AC to the memory operand. Again, opcode is 001, so that is D1. Let us write the register transfer statements for it. D1, T4. Now, we know that again, you cannot carry out any addition, subtraction, XOR operation directly on memory. So what we'll have to do? We'll have to first bring the memory operand specified by effective address to DR. Okay. So I also forgot to tell you one important thing. Look, this is a very important statement given over here. Note that the value of AC should not change unless the instruction specifies a change in its content. See, we generally use AC for carrying out some kind of operation. Okay. Unless and until you are told that the value of AC should change, you cannot change the value of AC. That is, you need to preserve the AC somewhere. You can use TR to store the content of AC temporarily, or you can exchange DR and AC. See, in the first instruction, we were making changes to AC only. Okay, so we did not take any care specifically for these two statements. But now look over here. What we are asked to do is we are asked to change the contents of memory word. So here what they mean to say is do not change the content of AC. Okay, you are asked to change the content only at memory. Please don't change the value of AC. So if I want to carry out any addition, subtraction, any kind of operation, I will need accumulator. The result of my ALU operation will also be stored in AC. So the old value of AC would be updated. So before we perform any operation on AC, what we need to do is we need to preserve the value of AC somewhere. Okay, so now let us see how to do it. Add AC to memory. So first of all, we brought the memory operand to DR because I cannot carry out directly addition with memory. Okay. Now, in the next step, D1, T5, what we need to do is, I need to perform AC equals to AC plus DR. But if I perform this step, AC equals to AC plus DR. Okay, what is DR? DR is M of EA. M of EA plus AC. Okay, so I need to perform this step AC plus DR. But now when I perform this step, what would happen? The old value of AC would be lost. So along with this, what I'll do is I will store the old value of AC to DR. Why am I not taking a step? Why did I not write this thing first? Sorry, why did I not? Okay, you need to first store. Wait, I'll write it like this so you can better understand. Okay, I write like this. It doesn't matter either you place it first or last, but first what I'll do is I'll store the content of AC to DR and simultaneously I'll perform this operation. How can this be done? This thing, can I do this thing simultaneously? To preserve the value of AC, this thing will take place through bus. And this thing, AC plus DR, will take place to ALU. So both these operations can be carried out simultaneously. So with the help of this step, you are preserving the value of old AC. And with the help of this step, you are actually performing the operation that is ADN. Okay, add to memory. So now this AC, after performing this step, my value of old AC would be stored to DR and updated AC will have the value M of EA plus AC. So now what we need to do is, now AC has the addition value. Now the next step, that is the last step required is, see, अभी तक हमने जो addition किया, that addition is in AC and not in memory. So now I'll have to transfer that value. I'll have to transfer the value of AC back to memory. Okay, And along with it, I will also have to replace the value of AC which we had temporarily stored it in DR. So now my AC again will have the old value itself, and the instruction is complete. So we'll also set the sequence counter to 0. Did you understand what did we do? First of all, we brought the operand M of EA to DR. Then to preserve the value of AC, we shifted the value of AC to DR, and then we performed the operation AC plus DR. After completion of this thing, we stored the updated value of AC to M of EA, and simultaneously we shifted the value of DR to AC. So this thing will take place through bus, and this thing will take place to ALU, transfer operation. Okay, so both steps can be done simultaneously. I'll not have to take another clock pulse for doing this transferring task. Okay, so now let us see the third instruction. What is our third instruction? Subtraction. In subtraction, you are asked to carry out AC equals to AC minus M of EA. Let us do that. It is 0, 1, 0, so D2. In subtraction, what we are asked to do? AC equals to AC minus M of EA. Now we know that subtraction cannot be done directly, so we'll have to perform it using 2's complement method. Okay, so D2, T4. Why D2? Because code given was 0, 1, 0. At this step, first thing what we need to do? Memory. So we need to bring the operand to DR. So DR equals to M of EA. Now I have the operand in DR, D2, T5. What will we do here? I need to, how can you perform AC minus M of EA? How do you perform it? You first take complement of it. Then you add 1 to it. And whatever answer you get over here, you add it with AC. Okay. So here what we will do is, you cannot carry out, you cannot complement a value. What does CMA instruction do? It complements the value of accumulator. I have my operand in DR. I do not have any facility for complementing the value of data register. Okay, so to complement this value, I will have to first bring this value to AC. Okay, because we have an instruction which can only complement accumulator's value. So what we'll do is, we'll bring the content of AC to DR. But when I complement this value, sorry, DR to AC, okay, this DR will bring it to AC, but when I bring this DR to AC, what would happen? My previous value of AC will be lost. So instead of bringing DR to AC only, we will also transfer the content of AC to DR. That is, we will be swapping the content of AC and DR so that we can preserve the value of AC. So how will we do that? Here, we will write DR to AC, AC to DR. Can I write these two steps simultaneously in a single clock pulse? Yes. Why? Because AC to DR will take place through bus, and DR to AC through ALU transfer. Okay. So both the steps can be done simultaneously. Now D2, T6. Now I have my operand in AC. This M of EA first got transferred to DR. From DR, it got transferred to AC. So now I will have to take complement of AC. So in this step, what I'll do is, AC equals to AC complement. Now I have the complemented value. अब क्या करना होगा? I'll have to increment the value of AC. Why? Because subtraction is carried out using 2's complement here. So now this AC will have the updated value of my memory operand. DR will have the old value of AC. Okay, so in the last step, what we will do, we will simply perform addition of AC and DR. This DR was having the old value of AC. Now this AC plus DR will be saved to your accumulator, and your instruction is completed. What was the instruction? Change the value of AC. Okay, so here my AC will have, current AC will have AC minus M of EA. So how many steps will I take place? These are the steps that are taking place. First, M of EA to DR, Then swap AC to DR and DR to AC so that my old AC is required here. Why? Because you need to subtract M of EA from the old AC only. So here we are swapping them. After swapping, take complement of your AC, add 1 to it to find 2's complement, and then add it to DR. So this would end my instruction sum. Fine? Chalo, now let us see the next one. Next is XCH. XCH, they have said that in XCH what you are asked to do is you are asked to swap, exchange memory word and the content of accumulator. दोनों का swapping करना है आपको. Okay? And the code given to you is, opcode given to you is 011. 011 is B3. So if I want to transfer the content of M of EA memory word to AC, I do not have any direct connection from memory to AC. So what I'll do is first bring it to DR. First bring the content of M of EA to DR and then swap DR and AC. Okay, D3, D5. So now you have it in DR. So DR may say whatever you have in DR, bring it to AC. And whatever was in AC, send it to memory. Again, both of these can be done at the same time. Why? Because this will take place through your ALU and this will take place through bus. Instruction is done. The content of memory is stored to AC via DR and content of AC can be directly sent to M of EA through your common bus. So my instruction is done. Set the sequence counter to 0. Was it easy? Okay. Moving to the next one. SEQ. SEQ stands for skip if equal. So here they have told us that if M of EA, that is if the memory word and AC, content of memory word and AC are equal, then skip. Skip means what? Skip the next instruction. PC equals to PC plus 1. Okay, so now let us see how to do this. Again, the code given to you is 100. Opcode is 100. So that is D4, T4. Here again, if you want to, okay, how do you compare? How can the comparison between two words, two binary numbers take place? Yes, XOR. Okay, so if I take XOR of 1 XOR 1, what is 1 XOR 1? 0. 1 XOR 0, 1. Okay, so what you can do is, you can check the value that if perform XOR on a particular operation, if it is 0, perform XOR of the two operands M of EA and AC. If it is 0, it means what? Your these two are equal. Your operands are equal. Okay, so here if I want to check, if I want to perform XOR on M of EA and AC, I'll first have to bring M of EA to DR. So in the first step, what we will do is M of EA to DR. Then to perform XOR, when I perform XOR in these two operations, the answer, whether it is 0 or 1, would be stored in AC. So again, I don't want to lose the value of AC. So क्या करेंगे? Either you transfer your AC to DR. So either I can write like this, AC to DR, and then AC equals to AC XOR DR. Okay, so here old AC would be stored to DR. Old AC would be stored to DR. Sorry, your DR would be, DR has M of EA. Sorry, so here I'll need TR. Okay, I'll transfer my content to TR, temporary register. And then I'll perform the XOR of AC, whatever is in AC right now, and DR. Okay, the answer I will be getting either 0 or 1 would be stored to AC. Now, at T6 clock cycle, what we will do? We will check. If AC is 0, then what do we need to do? PC equals to PC plus 1. And at the same time, Can I do this? Here we are just checking and incrementing the value of PC to the increment pin present in PC. Okay, so at the same time, can I bring my old AC back so that my value of AC doesn't change? If I don't do this, AC की value 0 या 1 हो जाएगी, which I don't want. I want to preserve the old value of AC. Okay, so here what did we do? Whatever we had stored the value of AC temporarily in TR, we are bringing it back to AC. And my task is done. So sequence counter 0. Okay, so this is SEQ. Skip is equal. We brought the content of memory to DR, AC to TR, then we performed EXOR operation, and then if the value of the operation is giving you 0, it means they are same. If they are same, skip. Skip means what? PC equals to PC plus 1. And the last question given to you is, what is the last one? Okay, BPA. What is BPA? This is B5, 101. So here they are saying that branch is AC is positive and non-zero. Okay, let us write the register transfer statements for this. BPA. Here you need to check if accumulator is greater than 0. That is, it should be positive and non-zero. Okay, so if your accumulator is greater than 0, then branch. How would we branch? Save the effective address to PC. Whatever address we provide to PC, you will be branching to that particular location. Okay, so let us write the code given to you was 101. So here my control function will be D5, T4. Here I need to check the content of accumulator. It should be positive and non-zero. So I will check like this. If AC is not equal to 0 and AC of 15 is equal to 0. Okay. If AC is not equal to 0 and AC 15 is 0, it indicates it is positive. So in this case, what I need to do? PC equals to AR. Effective address is specified to AR. So PC equals to AR. Sequence, set the sequence counter to 0. Right? So this instruction would be completed only in a single clock pulse, T4. So here we are just taking the value of AC. It should be non-zero and most significant bit should be 0. If most significant bit of AC, not A, okay, this is AC. If most significant bit of AC is 0, it indicates that your accumulator is positive. Okay, and if these two conditions hold true, set the value of PC to AR. AR is your effective address. And then set the sequence counter to 0. Okay, so now these are the 6 different instructions other than the 7 memory reference instructions that you studied. Okay, you were asked to change the value, change the memory reference instruction, and we wrote the respective register transfer statements that are required for execution of these instructions. Okay, we have studied in our lecture session previously, we had studied and, add, load, store, bun, BSA, ISA. Okay, and we also studied how to write register statements for these 6 instructions. So total 7 plus 6. We have studied 13 different instructions. So similarly, you may be given any specific instructions. All you need to do is your common bus. The figure of the common bus should be fit in your mind. You should know when to transfer, from which register can I transfer to another register simultaneously, or it should take a different clock pulse. So if that picture of common bus is fit in your mind, you can write the register transfer statements in your own way. Okay, so this was just an example. Once you know how to write register transfer statements, any definition given to you, any instruction given to you, you will be able to frame the register transfer statements for it. Fine. So if you have any doubt in any of these, you can let me know.